We are about to commence our next insightful session. I kindly request all participants to take their seats as we prepare to delve deep into a session filled with enriching discussions and presentation. Your engagement is key to the success of this conference, and we look forward to your active participation. Without further ado, let's begin our next session. Before we start, I request everyone to take a moment to switch your mobile phones to silent mode. This will ensure an uninterrupted and focused environment for our speakers and fellow participants. Your cooperation is appreciated. Thank you. We are getting into our next technical session. The Department of Physics of MES Kalladi College came into existence from the very inception of this college in 1967. Pre-degree was the only course run by the department at that time. The teaching of subsidiary papers in physics started with the sanctioning of BSc Chemistry and BSc Mathematics courses. BSc Physics course was sanctioned by the university in 1993. With the commencement of MES Physics in 2001 to 2002, the department was upgraded into postgraduate level. The vision of the department is to empower the students to become researchers or knowledge providers in the arena of physics and to contribute to the needs of the society by providing an environment of learning and outsourcing to academic rigor and innovation. Looking ahead, Department of Physics has a very ambitious infrastructure development. The department has embarked on continual upgrading of its facilities. All these are in line with our desire to train holistic physics graduates that make positive contribution to our nation. At present, the department is at the onset of upgradation to a research department. It is an honor to introduce our next distinguished speaker, Dr. S. Rajashabala. She is an associate professor and the head of the Department of Theoretical Physics at the School of Physics, Madurai Kamaraj University, Madurai. Dr. Rajashabala is a respected authority in the field, and today she will be sharing her profound insights on the topic, computational modeling of nanomaterials for technological applications. The entire family of MESKC bid a splendid welcome to the estimable chair of precision with a bouquet of acceleration. It's my immense pleasure to invite the Assistant Professor of Physics, Dr. Zainul Abadi, for chairing this session. May the session will be inculcate bounty of knowledge and give your insight with brilliant shine. Let us lend our ears to get an insight to the session adorned with precious intact and intimacy.
Good afternoon all. The next session, technical session, computational modeling of nanomaterials for technological applications by Dr. S. Rajashabala. He is an associate professor and head Department of Theoretical Physics, School of Physics, Madurai Kamaraj University. Rajashabala was a postdoctoral fellow at Uttala State University, Logan, USA, as an Indo-US German postdoc fellow, and in SRM University, Chennai, Tamil Nadu, and INSA visiting scientist. Dr. Rajashabala was the recipient of JNCASR Visiting Fellowship Program of Jawaharlal Nehru Center for Advanced Scientific Research, Bangalore. Dr. Rajashabala has 25 years of professional experience in the field of physics. She was the university nominee for the Board of Studies of Physics for various universities. Madam, Dr. Rajashabala in the field of specialization including low-dimensional quantum well systems, computational modeling, green energy harvesting and storage, energy and environmental remediation applications. Dr. Rajashabala has more than 60 published journals, published papers in nationally and internationally reputed journals, and more than 80 presentations or publications in national or international conferences. I welcome Dr. S. Rajashabala to handle the session on the computational modeling of nanomaterials for technological applications. Madam, please.
audible? Thank you, Dr. Sainu, for your nice introduction about me. First of all, I would like to thank audible. Okay. First of all, I would like to thank the management, college authorities, and the organizers for providing this golden opportunity to share some of my research findings with the young budding scientists. Okay, I am Dr. S. Rajashabala, working as Associate Professor in the Department of Theoretical Physics, Madurai Kamarajar University. The title of my talk is Computational Modeling of Nanomaterials for Technological Applications. In the recent years, the first for searching novel materials towards technological applications such as gas sensor, biosensor, and energy storage applications is augmented among scientific community. Computational material science is considered as a boon nowadays because the research timeline, research cost, and wet lab experiments could be minimized in order to identify the active sites and reaction mechanisms for technological applications. So far, carbon-based materials are utilized for gas sensor applications, biosensor applications, and energy storage applications. The realization of boron nitride nanostructures could enable them to find better place in the realm of technological applications due to their several unique properties such as fast response, ability to withstand at high temperatures, operate at harsh environments, and so on. Before entering into nanostructures, first of all, we must know what is matter. So both the physics and chemistry students well are of the concept of matter. Okay, matter means it is nothing but it possesses some mass and occupies some space. Okay, based on the physical and chemical properties, materials that is matter is classified into materials can be classified. So based on physical properties, the matter can be classified into primarily three categories. Okay, first one is solid, liquid, and gas. Fourth one is also there. What is that? Plasma. Okay. So based on chemical properties, the matter can be classified into homogeneous substance and heterogeneous substance. Okay. So I have focused only on the state of matter, based on physical properties, because the physicists only focused on solid state physics. Okay, so in this case, the solid. Okay, the solid is in this solid, the particles are closely packed. Okay, in liquid, the particles are loosely packed together. In gases, the particles are very loosely packed together. Okay, these are the main differences for the gaseous state, solid state, and liquid state. Okay, so these explanations are very mandatory for when you are studying the statistical mechanics. Okay. Okay, so based on band gap, the solid materials can be classified into three categories based on semiconductors. Okay, in the conductors, so first of all we must know what is band gap. Okay, band gap is the energy difference between top of the valence band. Don't say that it is the energy difference between conduction band and valence band. This is not correct. Okay, so it is the energy difference between top of valence band. This is the top of valence band. This is top of valence band, and this is the bottom of conduction band. So the energy difference between top of valence band and the bottom of conduction band, which gives band gap. Okay, based on the band gap value, materials classified into 3 categories. So in this case of insulators, you can see that the band gap is very large. Usually it is in the order of 7 electron volt. Okay, for insulators. Okay, insulators the gap is very high. So if the band gap is very high, there are no electrons available in the conduction band for the process of conduction. So there is no conductivity for this material. So it's said to be insulators. Okay. So in the case of conductors, you can see the overlapping of valence band and the conduction band take place. So there is no band gap in the case of conductors. There is no band gap in the case of conductors. Here, but a large number. So here, more number of electrons are available in the conduction band. So it is act as a conducting material. So all the metals are example for conductors. Okay. So here, in the case of semiconductor, the conductivity lies between the electrical conductivity. Conductivity means many conductivities are there in the. So here we are talking about electrical conductivity. Okay. Based here, this electrical conductivity of semiconductors lies between insulators and conductors. So here the band gap is minimum compared to which one? Insulators. Okay. So here the conductivity is low compared to insulating material, conducting material. Okay. So the examples for the semiconductors are all the 4th group elements are semiconductors. Okay, silicon, germanium. Okay. So the example for conductors, all the metals are examples for conductors. What is the example for insulators? Plastic, wood, mica. Okay. So these are all examples for which one? Insulators. Okay. So next we come into nanomaterials. So we know what is metal, what is material, solid material. So next we will discuss about nanomaterial. So nanomaterials are materials with at least any one of the dimension in the nanometer scale. Okay, nanometer range. Okay, it should be in the nanometer range. Don't say that nanomaterials are materials having dimension in the range of nanometer. It is not at all correct. Any one of the dimensions should be in the nanometer range. So then what is the nanometer range? Means 1 to 100 nanometer. So the nanometer should be in 1 to, and the nanometer means nanometer means 1 to 100 nanometer. Okay, here. So these nanomaterials properties are totally different from bulk materials. Bulk materials means 3-dimensional materials. Okay, so the properties of nanomaterials are totally different from bulk materials. So these nanomaterials will have large surface area, low melting point, and unique electrical, optical, and magnetic properties. Nanomaterials can exist in amorphous nature, polycrystalline nature, metallic nature, polymeric nature, ceramic nature, and so on. Okay. So these nanomaterials will have tunable electrical and optical properties. Tunable electrical, optical, and mechanical properties. So you must know tunable, optical, electrical, chemical. In general, you can say that tunable, chemical, physical, and mechanical properties in general. So you know that nanoparticles exhibit the size-dependent properties. That's the meaning. Size-dependent properties. So based on the dimensionality, based on the dimensionality. Nanomaterials are classified into 0-dimensional material, 1-dimensional material, 2-dimensional material, okay, and 3-dimensional materials. So the 0-dimensional, the examples for 0-dimensional materials are quantum dot, and fullerene. Okay. So the size of the quantum dot should be in the range of 2 to 10 nanometer. The size of the fullerene should be in the range of 1 to 100 nanometer. So the size should be 1 to 100 means it's a fullerene, 2 to 10 means it's a quantum dot. Okay. In the case of 1-dimensional material, the examples are nanotube, nanowire, nanorod. Okay. So all these three are examples for 1-dimensional materials. For 2-dimensional material, you can have any nano sheet. It may be graphene sheet or it may be boron-naked sheet. So all the nano sheets are examples for 2-dimensional materials. Here we consider the 3-dimensional material. So 3-dimensional material, the example for 3-dimensional material is graphite. Okay, graphite means it is a layered structure of graphene sheet. Okay, so it is a stacking of graphene sheet, many graphene sheets. So it is an example for 3-dimensional material or bundle of nanowires. Okay, they will make 3-dimensional material. Next, we will see what do you mean by quantum dot. So yeah, we know that quantum dots is an example for 0-dimensional material. Okay, quantum dots are nothing but nanometer sized semiconductor crystals with sizes below 10 nanometer, or the size should be in the range of 2 to 10 nanometer. Okay, the size should be in the range of 2 to 10 nanometer. The size means the size of the quantum dot means you can say that it is the diameter of the quantum dot. So the diameter of quantum dot should be in the range of 2 to 10 nanometer. These quantum dots, generally the quantum dots are called as artificial atoms. Why it should be artificial atom means the energy levels are discrete. Okay, usually the energy levels may be continuous or energy levels may be discrete. You can know that for the hydrogen atom, you studied the energy levels, no? Okay, the energy levels are discrete one. Okay. Here, the larger quantum dots with a diameter 5 to 6 nanometer emit longer wavelengths with orange and red color. So larger quantum dots with a diameter of 5 to 6 nanometer can emit red color or orange color. Okay, but smaller quantum dots emit shorter wavelengths with the colors of blue and green. Okay, so if you increase the size of the quantum dot, it can emit different colors. It can emit different colors. If the size is 2 nanometer, it can emit blue color. If it is 4 nanometer, the quantum dot size is 4 nanometer, it will emit green color. If the quantum dot size is 6 nanometer, it can emit red color or orange color. Okay. So here, why I am saying that it is a larger quantum dots emit longer wavelength or lower frequency. Longer wavelengths means in the nuclear spectrum. Which one has the longer wavelength and which one has shorter wavelength, whether violet or red. Red has longer wavelength, okay, or high wavelength. So here, if the wavelength is high means the frequency will be low, because what is the formula connecting frequency and wavelength? V is equal to mu by lambda, okay. Next, boron-naked nano cage. The fullerene can also be called as nano cage. Fullerene can also be called as nano cage. Here I consider boron-naked nano cage. You are well aware of carbon cage. That is C60. C60 is a Buckminster fullerene. Okay, it contains 60 carbon atoms. Okay, so here I consider boron-naked fullerene. Boron-naked fullerene or boron-naked cage. You can say it like that. Here boron-naked means it is an organic cousin of graphite. Boron-naked is an organic cousin of graphite. Graphite is made up of carbon atoms. Boron hydride is made up of boron and nitrogen atoms. So here the boron and nitrogen has equal number of boron and nitrogen atoms. In general, boron nitride contains equal number of boron and nitrogen atoms. So in general, variety of boron-related non-cage structures are exist for N is equal to 12, N is equal to 16, N is equal to 24, 36, 48, etc. So larger boron-related non-cages are also possible. Here, the general formula for representing the non-cage is Bn subscript n. Depends upon the small n value. You can say that whether it is a B12 N12 cage or B16 N16 cage or B24 N24 cage or B36 N36 cage. Okay, with the number of n value increases, small n value increases, the size of the cage will also increase. Okay, so here I have given 4 boron-nitrogen nano cages. We have calculated the formation energy by making use of density function theory calculations. We found that the formation energy for getting this structure is minus 953. For B16 N16, the formation energy is minus 1274. So the size of the nano cage increases, the formation energy also increases. Okay, size means because of the small n varies. If the small n varies now, the size of the nano cage also increases. Okay, so here so in all these 4 nano cages, this one B12 N12 is the most stable nano cage. Most stable Bn nano cage. Why it is most stable means the negatively the formation energy is maximum. Okay, negatively the formation energy is maximum. Okay, compared to all these 3. Okay, so this is the most stable nano cage compared to other 3 nano cages. So that's why in all our calculations we consider B12 N12 for our further study. So this here I also showcased the B12 N12 nano cage. It has 8 6-membered rings. So here this is a 6-membered ring. This is a 4-membered ring. So in general, the B12 N12 nano cage contains 8 6-membered rings and 6 4-membered rings. Next we pass on to nanowire. Nanowire is nanowire, nanorod and nanotube are examples for one-dimensional materials. So nanowire. So this figure shows the structure of nanowire. The nanowires are one-dimensional anisotropic structures. Why it is said to be anisotropic structures? Because the length and breadth will be different. So that's why it is anisotropic structures. The diameter should be 10 to 100 nanometer and the length of several micrometers. So length should be very large and diameter should be in the range of 10 to 100 nanometer. That's why I said that nanomaterials are any one of the dimensions should be in the nanometer range. Okay. Other dimensions will be in micrometer range. No problem at all. Then nanorod. Okay, nanorods are nanoscale structures with each dimension lies in the range of 1 to 100 nanometer. Here, nanorods are different from nanotube. Nanorods are similar to nanotube, but without internal surface. Okay, so here you won't find any internal surface because it is a rod. No, so rod means you can think that is there any internal surface. So within the tube, within the rod, you won't find any internal surface. But in the tube, you can find internal surface. Okay, so that's why it is a nanorod. Okay, so nanorod doesn't have any internal surface compared to nanotube. So here I showcase the boron-nitrogen nanotube. How do you get the nanotube? Okay, so nanotube is an example for one-dimensional material. But this nanotube can be obtained by rolling the two-dimensional boron-netted sheet. By rolling up two-dimensional boron-netted sheet, you can obtain boron-netted nanotube. So let us, for example, if you take any paper, any notebook paper, no, the notebook paper is a two-dimensional material. You can find length and breadth. Okay. So if you fold this paper, you can get a tube. Okay. So this is only example for one-dimensional material. Already I told that don't think that nanotube. Ma'am told that nanotube is a one-dimensional material. Ma'am, if we fold this paper, we can find length and breadth. But what is the definition for nano tube, nano rod or nano wire? What is it? Any one of the dimensions, any one dimension can be in micrometer range, but any one of the dimension must be in nanometer. அப்ப வந்து நம்ம breadth வந்து fold பண்ணால உங்களுக்கு என்னவா இருக்கும்? narrow ஆயிடும். அப்பதான் உங்களுக்கு அதனால internal surface இருக்காது. புரிஞ்சுச்சா? ஐயோ I'm talking in Tamil. Sorry. Okay. So you can, what is it? So when you fold this tube, when you get your tube from sheet, you can't, the breadth will be very minimum. Okay, breadth will be minimum. So the breadth is in the nanometer range, length in the micrometer range. That's why it is said to be a one-dimensional material. So the tubular structure of boron-netted nanotube can be obtained by rolling up a two-dimensional hexagonal boron-netted sheet, which is analogous to the formation of carbon nanotube from a two-dimensional graphite. Okay, two-dimensional graphite sheet. Okay. So carbon nanotube can be obtained from graphite sheet. I think this is in the boron-netted nanotube. You can find BN bonds. You can find BN bonds. This is 4,4 boron-netted nanotube. It is said to be armchair boron-netted nanotube. This is a zigzag boron-netted nanotube. So here yellow color represents the boron atom, blue color represents the nitrogen atom. So here you can find BN bond, BN bond, BN bond. So boron-netted nanotube you can find BN bonds. In the carbon nanotube you can find CC bond. Okay. So in general boron-netted nanotube is an organic acid of carbon nanotube. In the boron-netted nanotube, we have the boron-netted nanotube can exhibit dipolar nature. Okay, it is an added advantage compared to the carbon nanotube. Okay, so here dipolar nature of boron-netted nanotube is nothing but this boron atom. You heard about what is the atomic number of boron? Atomic number of boron? 5. Okay, it belongs to third group element. Okay. This boron belongs to third group element and nitrogen belongs to fifth group element. Okay, so based on the group, we can say that how many valence electrons are there in the boron atom and how many valence electrons are there in the nitrogen atom. Because it is a 3. Boron is the third group. So if it is a third group, the element has 3 valence electrons. If it is the fifth group, it has 5 valence electrons. You can write down the electronic configuration for boron. Now you can write out. So 5. The atomic number is 5. You can write out the electronic configuration 1s2, 2s2, 2p1. So 1s2, it is a completely filled shell. There is the second cell, 2s2, 2p1. So it is unfilled cell. So number of electrons is 3. So the valence electron is 3. For nitrogen, how many valence electrons are there? Already it belongs to fifth group. It is belong to fifth group. So 5 valence electrons are there. So when you write the electronic configuration, atomic number for nitrogen is 7. 1s2, 2s2, 2p, 3. Okay. So 1s2 completely filled. So second cell is 2s2. Don't consider that 2s2 is a completely filled cell. No, don't consider that one. You have to focus on first cell is completed. Second cell 2s2. Second cell, the number 2 is not completed. So that is 2s2, 2p1. Okay. So the 2p3 or 2s to 2p3. Okay, so the number of valence electron is 5. Okay, so we can say that compared to boron, nitrogen is electron rich atom. Nitrogen is electron. How many electrons are there? Valence electrons. How many valence electrons there? The electronic configuration. So 5 electrons are there. In the boron, 3 valence electrons are there. So which one has more electrons? Nitrogen. So nitrogen is electron rich atom. Boron is electron deficient atom. So that's why boron exhibits B plus and nitrogen exhibits N minus. So that's why boron-nated dipolar nature. Okay, dipolar nature. Carbon nanotube you cannot find the dipolar nature. So if it has dipolar nature, it will have spontaneous dipole moment. Okay. So this boron-nated nanotube has superior mechanical strength, high thermal conductivity, high chemical stability. It offers high resistance to oxidation and biocompatible. So it is a biocompatible material and chemically inert, very chemically inert. That's why high resistance to oxidation. Single bond boron-nated nanotubes are classified in terms of chiral angles and chiral indices. Okay, based on the chiral angles, it can be classified into non-chiral nanotubes and chiral nanotubes. Non-chiral nanotube means the chiral angle should be 0 degree and 30 degree. If the chiral angle is 0 degree means it is said to be zigzag boron-nated nanotube. If the chiral angle is 30 degree means it is an armchair boron-nated nanotube. For chiral nanotubes, the chiral angle can vary from 0 to 30 degree. Okay, so we are mainly focused on non-chiral nanotubes. Non-chiral nanotubes, that is zigzag and armchair tube. So for obtaining a zigzag, the angle should be 0 degree. So this picture represents how the angle theta is 0 degree or 30 degree. Then boron-nated nanosheet. Boron-nated nanosheet is an example for two-dimensional material. Okay. So the hexagonal boron-nated the hexagonal boron-nated is often compared to graphite. BN sheets may contain either zigzag or armchair edges or both. So sometimes the BN sheets, boron-nated BN sheets may contain zigzag sheet or armchair sheet, or it contains both armchair and the zigzag sheets. Here you can see. Here I have shown the boron-nated nanosheet. Okay, already told that boron-nated means it contains equal number of boron atom and nitrogen atom. You can count all these atoms. The number of atoms of boron and number of atoms of nitrogen will be equal. Okay, here already I told that yellow color means boron, blue color means nitrogen. Here I have given some gray colored atom. This gray colored atoms are nothing but hydrogen atom. Here I attached the hydrogen atom at the edges. Why I have attached the hydrogen atom at the edges? Okay, in general, every boron atom has to be connected with the 3 nitrogen atom. Similarly, every nitrogen atom has to be connected with the 3 boron atom because it has sp2 hybridization. Boron-nated has sp2 hybridization. So sp2 hybridization means it has 1 s orbital and 2 p orbitals. So it will make 3 bonds. sp2 hybridization means it has 3 bonds. So that's why every boron atom, this focus on the yellow color. So this boron atom connected with the first nitrogen atom, here one nitrogen atom, another nitrogen atom. So you can find every boron atom is connected with the 3 nitrogen, or every nitrogen is connected with the 3 boron atoms. But at the edges you cannot find all the nitrogen atom and the boron atoms are connected with the 3 boron or 3 nitrogen atoms. So in order to avoid the tangling bond effect, we have attached hydrogen atoms. So it is a dummy atom. You can think that it is a dummy atom, it creates one more bond. Here you can see only BN, two BN bonds are there at the edges. Edges. This is one BN bond, another BN bond. So this is which one? BH bond. Similarly, some other cases you can find NH bonds are also there. But in general, we should have 3 bonds. And moreover, already I told you that BN sheets may contain either zigzag edges or armchair edges or both edges. Here you can find, we have given, so this boron-laden nanosheet has zigzag edges. Here you can see zigzag. Okay, here armchair side. Which one? This one. This is armchair. You can find how I am marking, please note it down. This is armchair. You have to go to this point also. Similarly, you have to go to this point. So if you connect all these points, you can have armchair. So if you are only sitting on a chair with the arm, it's an armchair boron-laden nanosheet. Okay. So here all the edges, edges of the zigzag armchair are also present. Zigzag means just here BN edges. You can go like this way. Okay, zigzag. So these boron-laden nanomaterials can be utilized in the case of gas sensor applications, biosensor applications, and energy storage applications. So what do you mean by gas sensor? Gas sensor plays an important role for the detection of toxic gases present in our environment. Okay. So any gas sensor should have fast recovery, high sensitivity, high selectivity, and high stability. Gas sensor finds its application in the defense sector for monitoring the food quality, that is food spillage. Then it is used in the health sector by the analysis of exhaled breath and environmental monitoring. Okay. So in the defense sector, whether the food is whether the quality of food is good or not, we can check it by making use of gas sensor, because the spoilage food may emit some gas. No, that's why from the emitted gas we can check that whether the quality is good or not. And then health monitoring sector. So if a drunkard goes, whether the person is a drunkard or not, we can check it by checking his exhaled breath. Okay. So environmental monitoring. So in the during Diwali festival times, you can find that the environment is highly polluted. Okay. So we can say that we can check whether some changes are visible, some changes are may not visible. So and that, in that case we can use gas sensor. So for example, I have given that example, and which one, how the environment is polluted during Diwali times. We can this change we can easily find out. Okay, some of the cases, suppose the gas emission, which one, toxic gas emission from septic tank, we cannot see by our naked eyes. No, we are only by smelling only. Okay, only by inhaling that gas, toxic gases, we can say, we can realize that this one is only toxic gas. Sometimes even we don't realize. When we are sleeping in the air conditioned room, okay, if we emit some toxic gases, we cannot even realize that before that we will end up our life. Okay, so many nanostructured materials have been utilized for gas sensor applications. That is the carbon nanotube, graphene sheet, and metal oxide nanoparticles for the detection of NH3, CO2, PASG, N2O, and so on. The boron-laden nanomaterial have been effectively utilized for the detection of ammonia, NO2, CO2, oxygen, carbon monoxide, hydrogen cyanide, SO2, etc. So far, a variety of toxic gases have been detected to call our environment pollute-free. So here we consider the toxic gases. So in the environment, we can find enormous amount of toxic gases present in our environment. The toxic gases are ammonia, carbon monoxide, fluorine, hydrogen chloride, hydrogen cyanide, PASG, nitrogen dioxide, PASG, phosphine, sulfur dioxide, vinyl chloride, etc. So generally gases are harmful to living things. Accurate measurement of toxic gases is possible due to the development of nanomaterials for the gas concentration in the range of 100 part per million to 10,000 part per million. Okay, so among the toxic gases, hydrogen is the most toxic gases, even in the low concentration of 0.03 part per million. Okay, so even it is in the range of 0.03 part per million, it is a very toxic gas. But this hydrogen gas, that is in the N2H4. This is nitrogen, blue color represents nitrogen atom. So this is N2H4. This grey color represents nitrogen atom. So here, this, even though it is a toxic gases, it can be used as a fuel for rockets. And also it is used in the chemical industry, textile industry also. Okay. The inhaling of toxic gases may cause severe damage to liver, lungs, and kidneys. That's why it's said to be toxic gas. So biosensor, how the mononated nanomaterials can be utilized for biosensor. So for this, first of all, we must know what is biosensor. Biosensor means which converts biological response into electrical signal. We can sense the biological elements such as nucleic acid, enzymes, antibodies, microorganisms, cells and tissues. Here, which one? The commonly used biosensor are nothing but your BP meter and glucometer. These are nothing but your BP meter and glucometer are nothing but your biosensor. So this is BP meter is used to measure the body pressure, and this glucometer is BP meter of body pressure. Which one? Glucometer measures the sugar level. Okay, and also the thermometer is also an example for biosensor. One more point I have to mention. This one. When we are using any nanomaterial, we have to check whether the material has biocompatibility or not. Okay, this is an important point. So biocompatibility of nanomaterials is an important factor for designing a biosensor. So in our case, we sense the DNA nucleobases. Your DNA is nothing but it is a genetic material and deoxyribonucleic acid. The DNA nucleobases are adenine, guanine, cytosine and thymine. So the nanomaterials can also be utilized in the energy storage. Usually there is an energy crisis all over the world due to the fast growth of human population and industrialization. Okay, so hydrogen is considered a green and clean energy, and moreover it is a abundant element on Earth, most abundant element on Earth. Okay. So hydrogen can be used as an energy carrier. Usually the hydrogen can be stored as a gas or liquid form. The conventional method of storing hydrogen are compression, liquefaction. Recently, the solidification also possible by making use of nanomaterials. So the drawback of hydrogen as a gas or as a liquid, which requires high pressure tanks for storing hydrogen as a gas, and which requires cryogenic temperature of -252.8 degrees C for storing hydrogen as a liquid. So these are all considered major drawbacks for the conventional methods. So in the solidification of hydrogen requires nanomaterial. Okay, so here the solidification, the storing of hydrogen is possible only because of fission process or desorption process. Fission means the storing of hydrogen physically. Okay, storing of hydrogen. So fission means there is a weak interaction between absorbent and absorbent. That is means there is a weak interaction. That is van der Waals force will exist between hydrogen molecule and your nanomaterial. In the case of chemisorption, we can the interaction between a hydrogen molecule and nanomaterial will be covalent bond. Okay, so, interaction will be very strong in the form of covalent bond formation. Moreover, the fission is this process is a reversible process. This chemical fission is a irreversible process. You cannot get back all these things. So it was irreversible process because of the chemical bond formed is difficult to break it, because the chemical bond is nothing but the covalent bond. Breaking of covalent bond is very difficult because covalent bond, when do we get the covalent bond? Sharing of electrons between the atoms. Okay. So for storing of hydrogen in a nanomaterial, we consider metal hydrides. Metal hydrides are rich in hydrogen atoms. Okay, so these are all examples for metal hydrides. Magnesium hydride, lithium hydride, sodium hydride, and beryllium hydride. So you can see the H2 means nothing but hydrogen atom. So it already inbuilt, it has the hydrogen atoms. So we are storing this material as such in the chlorinated nanomaterial. Chlorinated nanomaterial. Okay, whether it is cage, whether it is tube or the sheet. So here the beryllium here, why we have considered only beryllium hydride means the beryllium is a highly electronegative element. If it is highly electronegative element means it can easily react with the hydrogen atom. Okay, so it can easily react with the hydrogen atom. So beryllium hydride is rich in hydrogen content. It has greater than 80% of hydrogen. In general, the beryllium hydride occurs as monomer, dimer, and trimer. Okay, monomer means BeH2, dimer means BeH2 twice, trimer means BeH2 thrice. Okay, so the format we have talked about the formation energy for beryllium hydride, dimer of beryllium hydride, trimer of beryllium hydride. Here you can see which energy is high in negative, minus 15.9 is the highest energy in the negative level. So it is the most stable system. Beryllium hydride monomer is the most stable system. So here I have showcased the beryllium hydride. So here I also beryllium hydride means BeH2. So this number is nothing but interatom resistance. Which one BeH? The resistance of BeH is 1.326 Angstrom. Okay. So in general, nanomaterials can be synthesized. Nanomaterials can be synthesized by adaptive nanotechnology. Which one? There are two methods are possible. One is top-down approach. Another one is bottom-up approach. So top-down approach means you are selecting a bulk material into a nanomaterial. Cutting down of bulk material into a nanomaterial is it's a very good example for top-down approach. So bottom-up approach means building up atom by atom into a nanomaterial means bottom-up approach. So here, this is one of the method for getting, this is a general theory for getting nanomaterials. So what experimentalists is doing is that they are synthesizing nanomaterials. But what theoreticians are doing that we are modeling nanomaterial by making use of some software. That is very complicated software, and also some software packages like Gaussian software, which one CAM software. Okay. So by making use of these softwares, we are calculating the various parameters of nanomaterial and modeling of nanomaterials and so on. So here, so I don't want to touch many things here. So in general, for modeling of any nanomaterial, if you want to find out any energy events, you should have to solve your Schrödinger equation. I think many of us well aware of Schrödinger equation. HSI equal to EC. I don't want to enter into this topic. HSI equal to EC. So, but all the physics and chemistry students must know what is a one-dimensional problem, one-atom problem or two-atom problem. Can you give one example for one-atom problem? One electron problem. Sorry, one-atom problem. One electron problem. One electron problem or two electron problem. Hydrogen atom is an example for one electron problem. Helium atom is an example for two electron problem. Okay. So here I consider many body problem. That means many body means many electron problem. So atoms with more number of electrons we will call this the many electron problem. So solving of 1 electron problem is easy using variation principle. Solving of 2 electron problem is very difficult using variation principle. Okay, so that is solving a Schrödinger equation. You can say that solving a Schrödinger equation using for a 2 electron problem. Okay, so yeah, why it is very difficult to solve a 2 electron problem is electron will have interaction. Okay, so we have to here I have written the Hamiltonian for the many electron problem. Here the Hamiltonian first term represents the kinetic energy part minus h cross del square by 2 NE. This is second term represents the which one? Kinetic energy of the nuclei minus h cross del square by 2 MK. Then this is the electron nucleus interaction. Electron, the charge of the electron is minus E. Then charge of the nucleus is ZE. That's why if you get this is the interaction between third term represents the interaction between the electron and the nucleus. Okay, the distance between the electron and the nucleus represented by RIK. Here charge of the nucleus is ZE, charge of the electron is minus E. So if you do the product of the charges now, minus ZE squared. So this case means interaction between the electrons. So electron means minus E into minus E. So electron interaction is this R. So another minus into minus plus, that's why you get it squared. So fourth term is represents the electron interaction. This is electron nucleus interaction. This is this one nuclear interaction. Okay, ZE into ZE. Okay, that's why E squared ZK is equal to L divided by RKL. Okay, RKL represents the distance between two nucleus. So you have to solve this equation for getting energy for a many body problem. So here in this case only you can find out the interaction between electron is also present. Electron nucleus is also present. Interaction between nucleus is also present. So all these terms will they complicate the solving of the Schrödinger equation. So that's why you have to need advanced workstation for solving Schrödinger equation. So even with your laptop or workstation, low-end workstation, you cannot solve this Schrödinger equations by making use of density function theory. Here I used the Gaussian software. The density function theory is implemented in VAST software and Gaussian software. The VAST software is mainly utilized by the physicist. Gaussian software is mainly utilized by the which one? Chemistry. Okay. So it gives the information about at a molecular level. Okay. So that here I utilized Gaussian software. Even though I am a physicist, I utilized Gaussian software. Gaussian is a computational software predicting properties of atoms and molecules and the electronic structure of many body problem. Okay. So here, one of the main, here I want to focus on only one application. Okay. Even though the materials are, the boron material and nanomaterials are utilized for gas sensor, biosensor and energy storage applications. Here I am going to focus only on one application. That application is a gas sensor application. Here the title I have given here is Aluminum doping makes boron material nanotube an attractive absorbent of hydrogen. Okay, so here I have sensed the hydrogen using boron material nanotube. What will happen when I replace one of the boron atom by aluminum? How it will detect the hydrogen? Whether it will detect the hydrogen effectively or not. Okay. So that's why I have given the motivation like this. Which one? Every day there is a shocking news about the sudden loss of human life due to the inhaling of toxic gases from uncleaned septic tanks, repaired air conditioners, automatic air conditioner vehicles, that is your air conditioner car. Okay. Then chemical industries and so on. So here, which one? When people exposed to toxic gases may suffer from irritation in eyes, irritation in nose and irritation in skin and respiratory problems. In some cases, the long-term exposure to less toxic gases may cause nervous problems, kidney-related problems, depression, headache and even death. Okay, the spillage of 30 tons of methyl isocyanate from Union Carbide India Limited pesticide factory at Bhopal has killed more than 50,000 people and affected over 6 lakh workers. So the Bhopal gas tragedy is considered as the world's worst industrial disaster. Okay, recently the Styling gas leakage from Visakhapatnam district affecting the lives of surrounding villages. So the gas sensor is inevitable to ensure the safety of human life. So here I consider assess, already I told that atrazine I am going to attach at the surface of boronated nanotube. Okay, so these are the reports available for, these are the previous reports available for my research work. Okay, boronated nanotubes such as 44, 55, 66, 80, 10,0 and 12,0 tubes. Which one? And also I considered aluminum doped boronated nanotube of 44, 55, 66, 80, 10,0 and 12,0 okay, so these are the tips I consider for my investigation. Here the boronated nanotube can be acted as the absorbent, that is a sensing material. Okay, it is a sensing material. So what I am going to attach at the boronated nanotube is the hydrogen. So it will act as an absorbent. So here I have all the calculation where you perform using Gaussian 09 software with B3LP. This is the best method for using density function theory, B3LP. So here I have showcased the results. Okay, I think you could be able to find out the values. So in the first 5, 1, 2, 3, 4, 5, 6 figures. First row 6 figures represent the pristine boronated nanotube. Okay, so here I have considered 4, 4 and then it's the counterpart 8, 0, then 5, 5, then 10, 0, 6, 6, then 12, 0. So I consider 6 different boronated nanotubes for the absorption of hydrogen at the surface of boronated nanotube. Here, in all the cases, I calculate the absorption energy. Absorption energy means how much energy is required to absorb the hydrogen at the surface of boronated nanotube. We found that the absorption energy is in the range of which one? Minus 7.9 kilocalorie per mole, minus 2.6, minus 2.1, minus 7.8, minus 4.1, then minus 1.7. Okay, so this is 4,4 boronated nanotube. This one is which one? This one is 8, 0 boronated nanotube. This is 5, 5. This is 10, 0. This is 6, 6. This is 12, 0. So these two are very much related with. This is answer. This is zigzag. That's all. So here in all the cases we found that as the diameter of the tube increases, okay, or the indices value increases, the absorption energy decreases. Okay, minus 7.9. So usually the absorption energy should be more than 10 kilocalorie per mole means the material is capable of sensing by hydrogen. Okay, but the calculated absorption energy was found to be minus 7.9 and up to minus 1.7. So these energies are very minimum energies. So the interaction will be, we can conclude that the interaction between hydrogen and the boronated nanomolecule is weak. Okay, so there is a weak interaction. If the energies are very low now, we can say that the interaction is weak. Okay, so and also we can conclude it from the interaction distance at the active site. Active site means the hydrogen molecule. So when the hydrogen molecule approaches the surface of boronated nanotube, it will try to make a bond. So where the hydrogen will make a bond means that site will be considered as an active site. So our interaction site. Okay. So here you can see. Here you can see 1.8 something or 1.6 something Armstrong value is there. So in all the cases, if you go from left to right, the interaction distance is also increases. So if the interaction distance increases means the interaction is weak. So for example, you can say that the interaction between myself and Sattana is interaction, the distance between myself and Sattana is minimum, interaction will be maximum. For me and the last row student, the distance is high. So the interaction will be weak. That's it. So you can also interpret it this way. So, and here in the second case we have replaced one of the boron atom by aluminium atom. Why I have replaced boron atom instead of nitrogen atom by aluminium in this case? In this, I replaced boron atom. Aluminium is a third group element. Boron is a third group element. So that's why I replaced boron by aluminium. But compared to boron, aluminium is a more reactive element. Compared to boron, even though boron and aluminium are in the third group element, aluminium is more reactive element. So that's why I replaced aluminium. Here, next table I will show you all these things. It is summarized in the table. Okay. Which one? So 4, 4, 5, 5, 6, 6 tubes are armature tubes. 8, 0, 10, 0, 12, 0 are zigzag tubes. So zigzag means it is represented by the index n, 0. This is the n, n. If n, the chiral indices are n, n or n, m means armature. N must be equal. In all the cases, n must be equal. That's why 4, 4, 5, 5, 6, 6. Here, any one of the value must be 0. That's why it is a zigzag tubes. Okay. So the diameter, so when we go from 4, 4 to 6, 6, the diameter increases. Here also 8, 0 to 12, 0, the diameter increases. So finally I have shown some value. This is for the BSC character energy. Don't bother about this BSC character energy. This is nothing but basis and superposition error is included in this correction. So we have carried out the BSC correction in the calculated absorption energy. That's why the absorption energies are in the range of -7.9 to -2.1. For this case, -7.8 to -1.7. So this energy -1.1, -4.1, -2.1, -2.8 absorption energies are very minimum. So these reactions are not possible. That's the meaning. We can conclude that the interaction is weak or the interaction is not at all possible. Because it is not at all experimentally observable quantity. Okay, if the energy should be greater than 10, you can say that this is possible experimentally. We are telling the experimental community that you can utilize this material for your sensor applications, or you can use this material for device fabrication. We are giving some suggestion based on our computational calculations. Okay, so when I did which one? Aluminum doping in the boronated nanotube, the absorption energies are increased by 4 times. Here you can see the absorption energy -35.8, 34.5. So compared to this one, the absorption energies are increased by 4 times. So you can say that the aluminum doped boronated nanotube will serve as a better sensor material than the pristine. Pristine means pure boronated nanomaterial. Okay, it's clear. So what I am concluding here is boronated nanomaterial is not suitable for sensing hydrogen, but the aluminum doped boronated nanomaterial is suitable for sensing by hydrogen. And this is what my conclusion. Which one? And one more important point is hydrogen. So here you can see 4, 4 and 8, 0. So what is the absorption energy I have given here? -7.9, -7.8. So these two boron-activated nanotubes these two boron-activated nanotubes have given the absorption energy in the range of -7.8 or 7 point something. So these two boron-activated nanotubes are called as isoenergetic systems. Isoenergetic, the two systems have this isoenergetic system or isoelectronic system. And because the obtained energies are almost same, -7.8, -7.9. Okay. So identical twins are same. It is very if it is difficult to distinguish both the twins, we can say that the all resemblance is 100%. We can say that these two tubes are which one? These two tubes are isoenergetic or isoelectronic structures. Boronated nanotube with hydrogen. Boronated nanotube 8, 0 or 4, 4. Okay. So here in this case, what we conclude here is the absorption energy is almost greater than -30. So you can utilize all kind of these tubes for the sensing of hydrogen. This is what we want to conclude. Okay. So all the tubes are suitable for sensing hydrogen. Here, this tube is okay. First tube is okay. Okay. So here, aluminum doped. It is an excellent tube. This is an excellent tube for sensing hydrogen. We can analyze whether the interaction is how the interaction takes place between hydrogen and boron material nanomaterial. Okay, so we can say that we can easily say that whether based on the interaction distance, whether the interaction takes place or not. Or for visualization, we are doing molecular electrostatic potential. We are plotting the molecular electrostatic potential. Here, this is what the molecular electrostatic potential for hydrogen. This is what the molecular electrostatic potential for hydrogen absorbed boron material nanotube. Aluminum doped boron material nanotube. Okay. So here, already I told that the boron is a electron rich atom or electron deficient atom. Electron deficient atom. So electron deficient means in the molecular electrostatic potential, the boron atom is represented by the red color. Okay. So that the red region only is due to the which one? Electron deficient boron atom. This blue region is due to the electron rich atom. That is your nitrogen. So here you can see the bulging of red region occurs at the interaction site. So you can say that from the molecular electrostatic potential, we can say that there is a strong interaction take place at the aluminum doped boron material nanotube. Okay. So these are all crystal boron material nanotubes. So based on the which one molecular electrostatic potential, we can easily distinguish whether it is a zigzag boron material nanotube or a armchair boron material nanotube. If it is which one? This is a zigzag tube. Here you can see a zigzag tube. Now, what is the beauty of the zigzag tube? Means all the columns will have same atoms. All the columns. So this is the first column, second column, third column, fourth column. All the columns will arrange by same atoms. So here, that's why you can find this one here. So here you can see the arrangement of red region, blue region, red region, blue region. See like that. Okay. So molecular electrostatic potential is only effectively useful for identification of whether the interaction is possible, whether the interaction is happened or not. Okay. So here we did biosensor applications using boron material nanomaterial. For this, we consider DNA nucleobases. So these are the nucleobases. Here we consider PN nanocage. I consider B12 nanocage. This is for the optimist structures of which one? B12 nanocage, which absorbs the adenine. We have attached adenine in 3 different places of the surface of boron material nanotube. Boron material nanocage. Okay, so this is boron material nanocage. So this is side view of my optimist geometry. So don't bother about this one. So here, when I attach adenine at the surface of the boron material nanotube, we obtain the absorption energies are almost same. So here the energy absorption means absorption energies are same means. So we consider 3 different absorption sites. Yeah, that's why we represent here nitrogen 33, nitrogen 25, nitrogen 29. Okay, so we consider 3 different nitrogen sites. So all these sites are favorable sites for attaching adenine at the surface of boron material nanocage. So these reactions are also possible. So what we did is we utilized boron material nanocage for sensing of DNA nucleobases. while attaching guanine at the surface of B12 N12, we consider the absorption site of nitrogen 30, nitrogen 36, and oxygen 32. So we consider three different active sites. So we consider only electron rich sites. Nitrogen and oxygen are electron rich sites. Okay. So here the calculated absorption energy was found to be minus 41 to minus 35 when we attach the three different places. So this is for the cytosine. We consider two different active sites, each one nitrogen 27 and oxygen 29. So here the calculated absorption energy was found to be minus 40 and minus 37. These energies are almost the same. So these sites are suitable sites are favorable sites for sensing by DNA nucleotides at the surface of boron-emitted nanoclouds. Boron-emitted nanocage as a storage medium for storing beryllium hydride as a molecule or as a cluster. Okay, we have considered beryllium hydride. Now, beryllium hydride can exist in monomer form, dimer form, trimer form. So it may make only cluster form or only molecules form. So when we attach, what will happen when we attach beryllium hydride as a molecule or a cluster at the surface of B12 nanocage? What will be the absorption energy? We calculated all these things. So I don't want to take much time. So here we attached beryllium hydride. Here we attached beryllium hydride. Beryllium hydride is BeH2. So this is the BeH2. This is my B12 molecule. Here I considered this one dimer of beryllium hydride. This is trimer of beryllium hydride. So when we attach all this trimer, dimer and monomer at the surface of B12 nanocage, the calculated absorption energy was found to be minus 46, minus 52, minus 53 something. Sorry, minus 83 something. So the absorption energies are very heavy. So these are experimentally positive. These reactions are experimentally positive. Or we can say that these reactions are experimentally observable reactions. So we use C20 nanocage. Carbon is the organic acid of boron-nitrate. So we consider C20. You cannot only take the number of atoms depends upon your vision. Because only we want to make a cage form. So if the minimum this is the most stable carbon, most stable cage. Okay, C20. You heard about C60. C60 is the Buckminster secondary and it has the 60 carbon atoms. So solving of 60 carbon atom is very tedious. It requires more time for getting a single optimized geometry. So this is all single optimized geometry. It will take 3 weeks or 4 weeks of time if you have, unless otherwise you have a high-end workstation. If you have a high-end workstation, you will get it within a day. Or you want to do it 2 weeks or 3 weeks. Okay. So you can imagine how difficult to get a theoretical value for a single case. So it needs patience first of all. So research means it requires patience. Okay. So we have utilized this carbon 20 cage also. So here also we found that the absorption energy was found to be minus 14, minus 66, minus 19. So when you attach monomer, this is dimer and trimer. So when you attach a trimer at the surface of C20, the adsorption energy was found to be in the range of minus 91 kilocalorie per mole. So actually, I am using usually this system we use the unit for energy is joule, electron volt, but here I am using kilocalorie or kilojoule per mole. So this is what actually this is when we are using thermodynamical parameters, when we are studying thermodynamical parameters, when we are doing thermodynamical study, we have to utilize energy, we have to represent energy in terms of kilocalorie or kilojoule per mole. Okay. So other than the unit for energy, that's all. So we have attached we have attached single monomer at one place, two monomers at two different places, three monomers. This is one monomer, we have attached three monomers at three different places. So here we found that the adsorption energy gradually increases. So as the number of monomer increases, so you can attach more number of monomers at the surface of mutual electrode non-activity. This is what my conclusion. Okay. So here also we attach monomers, a single monomer, two monomers, three monomers. Okay. So when we attach it to here, this is what on the C20 monomer absorbed C20 nanogauge. Here two monomers absorbed C20 nanogauge. Here three monomers absorbed C20 gauge. But when we attach two monomers at the nearby places, substance like means what will happen? It will make a dimer. So when we attach two monomers nearby means it will make a dimer. So the energy, corporate energy was found to be minus 111 kilocalorie per mole. So overall, this one. So the overall summary is that we have utilized boron-nitrogen nanomaterial for gas sensor, biosensor, and energy storage applications. So what is these three areas are very important areas. Are very important. We have to give more focus on these areas. So you can find out from the energy storage. Energy storage are you can find out from the hydrogen operated vehicles. No, hydrogen operated vehicles you can find out. Nowadays you can have the hydrogen operated vehicles are possible. Okay, because there is a scarcity of fuel cells. Okay, fuel cell fuels possible scarcity of possible, that is petroleum. We are lining up on the petroleum. Like this, we can do the petroleum power in the next 50 years or next 20 years. That's why we go for alternative methods. That's why we are using green energy. Green energy means which one? Even with cars, we can green color electric vehicles. Okay, hospitals now we can have electric vehicles. Even cars they have battery operated cars. So we are also gas sensor, biosensor, and which one? Hydrogen storage. So these are three areas are very prominent areas. The government is talking about large amount of fund for the development of these fields. Okay. So all these works are published in the MES Scholar So you got all the papers are published. If you have any questions, you can ask me.
Thank you, ma'am. The session is open for discussion. Those who have any questions, you can ask me.
Ma'am, you said that nanomaterials can be used in biosensors. Can you explain it? How is this as a body? You said that we can use nanomaterials for measure body temperature, pressure, glucose. How this work?
How does it work? How does it work? So that's why there is an interaction between our which one? And the material and the sensing material and we are getting there is an interaction that takes place between so there is an interaction take place between the nanomaterial and the sensing material. Okay. So இப்போ நீங்கள் சுகர் இது பண்ணுறோம்ல அங்கே சென்சிங் ஆகிறனால தான், அதாவது பயாலஜிக்கல் சிக்னலில் வந்து இது பண்ணுறது கன்வெர்ட்டிங் ஆஃப் பயாலஜிக்கல் சிக்னல் இன்ட்டு எலக்ட்ரிக்கல் சிக்னலாக இருக்கனால தான் நம்ம பார்க்க முடியும் பயோசென்சார்ஸ்.
Yeah, the research part I couldn't quite follow. But from the basis, you said that quantum dots have discrete energies. Could you explain what it actually means? I mean,
means energy levels are it has different energy levels. So it won't be continuous. அதாவது degenerate ஆகாது. ஒவ்வொரு எனர்ஜி இப்போ n is equal to 1. இப்போ ஃபார் எக்ஸாம்பிள் ஹைட்ரஜன் ஆட்டம் ப்ராப்ளம். Hydrogen atom problem is the energy is generalized by En is equal to minus 13.6 by n square into electron volt. If you put n is equal to 1, the nth first ground state will have different energy. N is equal to 2 state will have different energy. All the states will have different energy.
hydrogen atom is understandable because we are talking about an electrode confined inside
So we can.
Quantum dot is the collection of atoms.
So theoretically we are calculate no energy. That's why we can the Gaussian software is useful for getting the HOMO, LUMO energy level. No, you can find out only easily. There are softwares available, so we can calculate various energy levels.
It works with quantum dot like that. Wouldn't have a continuous set of energy.
What we are doing is just we are doing whether this boron-nitride nanotube or boron-nitride nanocage or boron-nitride nanosheet is suitable for sensing of any sensing of which one hydrogen or toxic gases or DNA nucleobases, biological element. Okay, so here we found that the interaction is maximum. If the interaction is, we cannot. So here, for example, boron-nitride means B12N12. B12N12, 24 active sites are there. And a B has 12 boron atom. Nitrogen 12 atoms are there. So totally 24 active sites are there. All sites are the active sites. All sites are suitable sites. But we got to check which one is more suitable. Okay, so based on the chemical environment also, the interaction will be maximum or the interaction will be big. So we have to check the suitability of the active site. So we have to choose the active site. Okay, so if the interaction in the active site, if we choose the proper active sites, I am not going to consider all the sites are active sites. For example, we attach hydrogen. Hydrogen means I have chosen nitrogen of hydrazine and boron of boron-nitride nanotube. So that's why it will make BN bond. Boron of boron-nitride nanotube, that is B atom. Nitrogen of hydrazine, nitrogen atom. Sharing of electrons will possible. So that's why it will make up with the BN bond or covalent bond. So if the interaction is maximum, means I can say that this interaction is possible. If the interaction is minimum in the absorption energy or interaction distance is absorption energy is minimum, means we can say that the reaction is not possible. In terms of interaction distance minimum means reaction is possible. Interaction distance larger reaction is minimum.
Talking about electromagnetic interactions or
it won't electromagnetic interaction just so whether it is on the sharing of electrons, interaction will take place via physics or chemistry. So physics means there is a peak interaction. weak interaction will take place. Or it will have a strong interaction. So strong interaction means the covalent bond formation. Or it can have hydrogen bond formation. Some cases we can notice the hydrogen bond formation also in the case of DNA nucleobases apart from BN bond formation. So we get more absorption energy in the case of DNA nucleobases because of the formation of hydrogen bonds and covalent bonds.
Coming back to this conversation,
Hydrogen atom problem means if it makes the covalent bond, it is not an added advantage. In the stored hydrogen has to be released, so it must have some weak interaction. So when we have weak interaction in the case of hydrogen storage, it is an added advantage. If it makes a stronger covalent bond, it will be treated as an active site.
I have a more basic question. You talked about absorption energy. It's given in negative.
Yeah, why we are having a so absorption energy is negative means, for example, hydrogen atom problem. You can say that the energy is represented by minus 13. E is equal to minus 13.6 electron volt by n squared. This negative sign represents the interaction. The interaction is an attractive interaction. It is an attractive interaction because electron and nucleus. So electron is a negatively charged particle, nucleus is a positively charged particle. So therefore we have a strong interaction. So if we have a negative sign, this interaction is a strong interaction. If we get positive value means it is a weak interaction. That's why it comes around minus 1.7. That means it is going to approach 0.
Absorption won't happen.
What's that?
Absorption won't happen.
If it approaches to 0 means no absorption will take place. So if minus sign represents the strong interaction exists between adsorbate and adsorbate. Positive sign means weak interaction exists between adsorbate and adsorbate. You can ask. So, for example, absorption energy means you have to calculate there is a formula for calculating absorption energy. First, we have to optimize the hydrogen molecule. For example, hydrogen absorbed boron-nated nanotube. So, first we have to do optimization for hydrogen molecule. We have to do optimization for boron-nated molecule, boron-nated nanotube. Then we have to do optimization for hydrogen absorbed boron-nated nanotube. So, we have 3 different optimization geometry. So, we have to find out after do optimization, it will give some energy. Okay, we have to search it. Where is the EMT energy? We have to search it. So, we have to substitute these values in our formula. That is absorption energy is equal to energy of complex minus within the bracket energy of boron-nated nanotube plus energy of hydrogen, which gives cohesive energy. We have studied cohesive energy. The cohesive energy, same formula is nothing but absorption energy. So it is it's a more even though it is theoretical, it gives excellent results. So we have to predict by our own literature knowledge.
This density function, how does it exactly deal with the many particle sorting? Even hydrogen atom is reduced into one particle problem and then
we want to go because here
how does it actually
for my case B12 N12. So how many atoms are there? 24 atoms are there. Then hydrogen means 6 2 H4 6 30 atoms are there. So 30 atoms are there. It will do optimization by making some which one with density function. These are many body problem. So these are all the softwares available for solving many body problem. That's why we came for density function. Otherwise we can use the same assignments with the Hamiltonian kinetic energy plus potential. So for solving up with the Hamiltonian, that is an equation for singular quantum problem is easy. That's why we are focused on density function. Density function is
Thank you, ma'am, for this insightful session. And thank you, sir, for your precious time. It's now our distinct invite our esteemed speaker, Dr. S. Rajashabla ma'am, to join us on stage to receive a token of appreciation. I invite Sarita ma'am, Assistant Professor, Department of Physics, to join us on stage for this honorable task. Thank you, ma'am, for your enlightening presentation and for being an integral part of our conference.
Once again, I thank you all for the nice hospitality. Thank you.
As we draw closer to the conclusion of this insightful session, we are honored to invite the session chair. I kindly request Dr. Zainul Abidin sir to come forward and receive the small token of it as a gesture of our gratitude for his significant contribution. I invite Sarita ma'am, Assistant Professor, Department of Physics, to join us on stage for this honorable task. Thank you, ma'am, and thank you, sir. Ladies and gentlemen, as we wrap up this Ladies and gentlemen, I would like to invite a respected member of our faculty to express our gratitude and appreciation for the insightful session we just had. I request Dr. Job Sabu, Assistant Professor, Department of Physics, MES Kalladi College, to come forward and deliver the vote of thanks.
A very good evening to one and all. I extend my sincere gratitude to each one of you for being an integral part of this enlightening session. And a very special thanks to our distinguished speaker, Dr. S. Rajashabla ma'am, Associate Professor and Head of Physics, Department of Theoretical Physics, School of Physics, Madurai Kamaraj University, for sharing her insights on computational methodology of nanomaterials for technological applications. And the way you presented the topic was really informative, well arranged, in such a way that she has explained all application levels like energy storage devices, energy sensors, biosensors, catalytic actions, drug delivery systems, all in a very good manner. The way she presented was really a model to each and everyone that we should encourage. I express my deep appreciation to Dr. Zainul Abidin, the Assistant Professor of Physics, who chaired the session, for presiding over the discussion and ensuring the smooth flow of these valuable ideas throughout the session. And I thank all the participants that truly enriched the session to be very meaningful. And once again, I thank you all on the behalf of MESKCON International Conference and MES Kalladi College, Mannarkkad. We thank you, ma'am. Thank you. Thank you.
Thank you, sir. Your words had undoubtedly captured the essence of our collective appreciation. Ladies and gentlemen, as we wrap up this engaging session, we invite you to a short tea break. Refreshments are available at the corridors of the conference hall.